Okay, so my name is Zachary Schneider, and I'm here to do a talk about modern software delivery. And first, just a little bit about me. Currently, I am operations architect at Instana Inc. We provide a SaaS solution for APM. Previously, I was at Boundary, operations architect again. Boundary was purchased by BMC. Again, systems infrastructure and monitoring. Prior to that, I was at Rackspace as working as lead operations engineer. I was part of the team that built cloud databases, which is Rackspace's version of RDS, cloud sites, and cloud DNS. So I built a few things. I've run a few things. But more importantly, I've developed the systems that delivered these things to our customers. So I wanted to talk about software delivery, not necessarily because I love the topic, but because I'm not satisfied with the current state of things. It's a challenging proposition, especially when you enter the realm of distributed systems. But in a nutshell, we can boil this down to some basic requirements. The biggest one is to create and enforce consistency in the systems you deliver. Delivery should always be repeatable. The results of your delivery should always be auditable, so you can validate, what's been done, what's been installed, and create an audit trail for that. It must be usable by the developer and the operator, and most importantly, it must be operable. Now, for us at Instana, we have requirements for in-house for our staff to develop and operate our software, but we also have to deliver these solutions to customers who may not be as well educated in regards to distributed systems operations or any of the modern, delivery systems such as containers, etc. So, a summary for this talk. I'm just going to go over, what I see as the components of software delivery, a few of the anti-patterns that I continue to see when venturing into new enterprises and new setups, the patterns, the triumphs and failures of these patterns. I'd like to talk briefly about usability in regards to system software. I think it's definitely lacking, at least in Linux community, and then what I perceive to be the solution going forward. So, for successful software delivery, I've implemented this. It follows the same basic pattern. So we have our version control system. Our build environment pulls the source from version control. We produce an artifact. This artifact is archived and hopefully cryptographically signed. And from these archives, we do our deployments. This pattern ensures that variability is only in one place. So it should only be in the build system. There's some caveats there. So if you're building native applications and you're linking dynamically, then obviously, if you have a difference between your build system and your deployment systems, there may be issues. However, for most people, especially if you're using dynamic runtimes like Java or .NET, this won't be a factor. The dotted line represents a security barrier, and this is essential in my mind because our build infrastructure should not touch any of our deployed environments. And that's not just production. It should be any functional, testable, deployed environment. So this could be staging for some people, or ad hoc development environments, or what have you. So the largest anti-pattern I see in regards to deployment was kind of popularized by Heroku, and mostly because I don't think a lot of people understand what goes on behind the scenes there. But essentially, we'll have some sort of orchestration, and we will pull directly from VCS and deploy to our environments. This probably doesn't happen too much in Java and .NET shops, but I see it continuously in Node shops, Ruby shops, Python shops. And this really isn't great, because what we've done here is, the variability is in our deployed environment. So what I mean by variability is we may not have all our versions pinned in whatever descriptor decides what's installed via npm. We also may be using native modules. So we've also turned our deployed environment into a build environment. So we're compiling npm modules or Ruby modules or Python modules on our production systems. There's also these neat features in these software package managers whereby you can pull or yank dependencies that other people may depend on. And one of the great examples was this Node left pad thing. I think everybody might know about that, but essentially there was a small 3-line function, I think, and a lot of people depended on it, and someone became angry and they pulled it, and it broke a lot of things. The other thing is you could be deploying and the software repos you depend on may just go offline. So you could say you had a 40 system deployment. Mid-deployment, half the system's deployed, half of it's not, and now you're in an inconsistent state. So this is just not great. And in regards to Heroku, this isn't really what happens. This is what the user perceives, but they do build artifacts and push them out and scale them out behind the scenes. So. Another great one that I've seen is building binaries locally and SCPing them around. I've seen people compiling from source on production systems with 2,500 line bash files, so that's pretty neat. Definitely not good for consistency. Deploying artifacts via SSH. So, SSH, yeah, you can use it as an RPC protocol. You can use it to move files around, but eventually, after you reach a certain systems threshold, this is not going to work for you. And this does include Ansible. So specifically at Instana, we were using Ansible to handle container orchestration. And after about 30 systems, you start to run into the fun problems with the Paramiko SSH library that sits underneath Python. And some systems will get rolled out. There'll be occasionally silent failures, etc. But generally, it may work at first, but eventually it'll probably not work for you. So let's get into some of the patterns. And I like to specify, containers on Linux specifically because my background is originally from Solaris, where we had actual containers, not namespaces and C groups, which is what we're calling containers on Linux. They're not the same. They don't provide the same guarantees in regards to reliability or security. So this is why there's the flag. So let's talk about the good things in regards to delivery with containers. So we're deploying immutable artifacts. This is great. So it follows the original component diagram that I showed. Our build infrastructure does not have to touch deployment environments, so that's great. And the build tooling is developer friendly, mostly. So let's talk about the bad. The bad mostly revolves around the operability requirement. The way the image layering was implemented, it just presents a lot of problems. Containers have been touted as this new technology that enables rapid deployment and rapid delivery. But the funny thing is, when you're using layers in images and you're deploying 30 or 20 to 30 times a day, you will quickly realize that this is a problem. Number one, because of space. And number two, the layering updates actually take a significant period of time, especially when you're going from scratch on a new system. So if I have to expand my infrastructure and I haven't pulled all the layers, all the dependent layers for an image, that takes a large amount of time. The other thing is the file system drivers are immature and they're kernel dependent. So a lot of people seem to use Ubuntu for deploying containers, and this is generally okay. However, on just about every container deployment operating system, with the device mapper, with AUFS, and with overlay, I've experienced kernel panics, either with customer systems or our systems at some point, and we've traced this back to the file system drivers. So I mean, I don't know about you, but I'm not a huge fan of installing software on a system and getting a kernel panic. That's just not great. Overlay 2 seems to work really well if you can get a 4.8 kernel. I don't know of a distribution currently that you can install out of the box with a 4.8 kernel. ZFS, oddly enough, works quite well on Linux, which is really funny because all these other file systems are native, and ZFS is not native to Linux originally, and yet it works well. So that's just an interesting little bit there. Immutability is an interesting proposition in regards to containers. Immutability to me means a different thing, I think. Now, I agree that with containers, your artifacts are immutable. I mean, you can't update an artifact in a repository unless you overwrite it or retag it or what have you. However, there's nothing immutable about containers once they're running. There were frameworks that allow you to code for this for Solaris, but I don't know of any that allow you to easily accomplish this on Linux. So there's really no guarantees after the container is running that something inside it can't be modified by a user or someone else. And actually, I've seen this. I've seen people log into containers, make a change, leave them running, and then the containers get restarted, change is gone, etc. So this is interesting. Security, I have a problem with this. So we have no real security by default out of box, especially with the Docker runtime. You have to configure it explicitly. So this will mean either building SE Linux policies, AppArmor policies. SecComp is the new one. I'm not up on that. I know it has better integration with Docker, but it just seems that these things should be provided by default instead of like a wrapper around these underlying services. I have a lot of experience with trying to run these things, these processes as non-root. And once you get into how Linux does the UID mapping from an unprivileged user to privileged users within a container, you quickly run into that morass. So just getting Postgres to work in a non-root container is a challenge, for example. And then finally, container builds. They really allow you to they allow you to do whatever you want. It's kind of like going back to Bash. So my Docker file is basically like my just a Bash script that builds these things. So, any sufficiently advanced container build, to me, it's kind of like going splunking in a garbage dump. I see files being grabbed from here and there. I see, software being downloaded, not necessarily verified. And this isn't necessarily because, people want to do bad things. I think it's more there's no facility to provide for the things that we really need to provide for in regards to auditability and validation in this container framework. It just hasn't been thought about. So you have to add it yourself. So in keeping with the theme of the conference, let's talk about the old new stuff. So operating system packages, and this is kind of what, after we encountered all the issues at Instana and at Boundary with containers and actually trying to deliver containers to customers, we decided to go back to packages, operating system packages. So apparently, and I didn't even know this, Package Source was the first in 1997 that offered a package system and dependency resolution in the installer. apt was a close second. Deb and dpackage was, I think it was around since 1994, but apt didn't become usable until 1998. Yum followed in 2003 for the RPM distros. And maybe not many people know about IPS, but IPS is the image packaging system that was developed at Sun for OpenSolaris. And it also, I think it was probably the most, it was, I guess I shouldn't say was, it's still in use in OmniOS, but it had some interesting features. Its main downfall, though, was that, again, difficult to build packages for, and you had to run a special daemon to serve your repositories. So let's talk about the good first. Again, we're deploying immutable artifacts, great. Build infrastructure separated from your deployed environments. Systems composed of packages can be cryptographically verified and repaired. Now this is every time someone invents a new software installer or software deployment system. Developers love to do this. I can install this software better, but this is the feature that's always missed. With one command, or maybe one or two commands, with any of these package systems, well, at least apt, RPM, and IPS, you can validate cryptographically every file on the file system that was installed with a package. And this is invaluable if you have customer-facing system, or internet-facing systems, rather, and maybe you think you've been compromised. So it's really important to, at the very least, validate the operating system and the software you yourself have delivered. And the more quickly you can do this, the better. So this is the main feature. And containers, you can sort of do this ad hoc. You can try and validate the software within the containers, but there's no comprehensive solution to type one command and be like, all right, this file was modified. It does not match what's in my archive. It does not match what we published. We have a problem. So package systems do this. And overall, they're easy to operate and maintain. So there's no daemon running that I need to ensure is there to deploy my software. I'm not going to get a kernel panic when I install a package, so that's nice. And the other great thing is that, especially in microservice land, small frequent updates are very fast. I mean, under 10 to 20 seconds, and this is kind of a boon for these frequent updates. So obviously, there's something wrong with this. Otherwise, everyone would be building packages, right? So the number one design flaw in every single package system ever created is that the creators have coupled the build methodology with the package system and or the package format. And this is a huge problem because, well, let's just use package source as an example. As a developer, when I just want to deliver software and get it out there, I don't want to adopt some messed up build system. And with package source, that would be make and M4. no one's going to do that. The other big issue is most of the repository metadata formats are not easily serializable. Okay, so this is not true for Yum. They do use XML. That's great. But I can kind of expound on this just a little bit. Okay. So let's check out Debian's package metadata and the stuff we have to do to build a Debian package. So here's the basic structure, and what Debian does is they grab the upstream tarball and they save the patches here. And then we have to provide these interesting files. So we have our control file that we have to create. Okay, this is an interesting format. There is a document that describes how to build these, but creating these programmatically without C or a bunch of Perl is difficult. It's white space significant, etc. Let's see what else. The changelog, yeah, the changelog even, and this is how you get new versions with the default Debian packaging tools. So this is white space significant and follows a certain format, and there are tabs and spaces in here you have to be aware of, so that's no fun. All in all, though, compared to what you can do with a Docker file, no one wants to deal with this, and it kind of goes on and on. And if you look at the documentation, there's quite a bit of documentation just to get started. So package source is kind of the same thing. I mean, we start out right away getting into make and preprocess make files and running 3 or 4 different commands to create the metadata. This is just painful. IPS is very similar. So this mainly revolves around creating a manifest for our package and then running 3 or 4 commands trying to change this. So, it's really difficult to generate these programmatically, and really all you want to do is deliver software, and no one should have to deal with this. So, yeah, and the file formats aren't much better. So, like RPM uses a CPIO archive. I don't know if you've ever dealt with the tools to manage that. The Debian archives are, interestingly enough, 2 tar-gz archives wrapped in an AR archive. Yeah, try finding a AR library in Java, for example, if you wanted to programmatically generate these. And in order to really efficiently deliver these things, we need to layer technology on top of this, and I'll talk about technology layering in a little bit. We use a program called FPM, and FPM basically, and this is the frustrating thing about it, it creates a DSL or provides a DSL so you can generate packages from multiple formats with one command. So, for example, I can do my build and generate a deb and an RPM if there's no architecture or native limitations, from the same build. And this is how we deliver packages at Instana and how we did it at Boundary. The other frustrating thing is the package versioning for the various package systems aren't driven by a single standard. So they're roughly similar. You can figure out your own versioning schemes. It'll generally work in each one, but it's not like it's actually SemVer backed by some sort of standard that you can read and reason about for every system. So, and the other big problem is there isn't one, well, besides package source, I guess, there isn't one package system that you can run on all your target platforms. But as we saw before, the package source build system isn't that great. So let's go back to usability. And this is mainly why I'm talking about this today. So in the Linux community, layering is kind of a big thing. So we developed this unusable or archaic system, and IP tables is a great example because I think everybody's had to deal with it. And then in order to make this palatable or usable, we layer things. So Ubuntu has UFW, or did, and now the new hotness is Firewall D, where we get to write little XML files that define, how our firewall is working. So okay, that's great. Why couldn't we just expose these things in the base system? And it's not that we can't. Other people do this all the time. So ZFS versus BTRFS, the usability difference is staggering. If anybody can tell me on a production system how much space I actually have on a BTRFS volume, I'll praise you, because I can never actually figure it out. OpenBSD PF versus IP tables, and I'll show this in a second, but this is an outstanding example of usability integrated at the base level with no layering. Solaris Crossbow versus Open vSwitch. Yeah. OpenBSD IPsec CTL versus free SWAN. So IPsec CTL is pretty amazing because you have a command line interface that you can use to set up tunnels. You have a simple config file. You can start and stop tunnels. You can interact with it while it's running. And free SWAN is just not even comparable. And just to illustrate the IP tables point, and this is kind of a benign example. I mean, this is simple, but at a glance, I can look at the PF example, and it's almost human readable. I can look at this and know what the hell is going on with this rule, right? So you can just imagine once you get more complex and something's going on, and I have a giant IP tables rule set, and I'm trying to look at this while 3 people over here are screaming this isn't working, and a customer is complaining over here. It's really just the benefit just manifests itself right there. I can look at this, I can glance at it, I know exactly what's going on. It's in a human readable form, and I can solve the issue. So usability in system software is important, and we don't seem to be achieving that in Linux land. So we want to move forward, and I'll go back to the original requirements. We want to fix software delivery. So again, create consistency, repeatable results, auditable results, the one everyone forgets. Must be usable, must be operable. So after having dealt with software delivery for 20 years, did a lot of prior art research, and got a working group to put together what we hope will be a better solution in the future for software delivery. So we called it ZPS. This is kind of a play on the whole ZFS thing, the last word in package management. We were going to use, make packages great again as a tagline, but I think it's too soon, maybe. Our number one influencers for the software is apt, IPS again, NPM. Yeah, it's a software module manager, not a binary package management solution, but there's a lot of good ideas there. And let's go into some of the principles. So obviously, it satisfies our requirements. Okay, developer and operator ease of use. Okay, so I want both camps to be happy. We want to support multiple operating systems out of box. It's not that hard to abstract the elements of software installation. And one of the core ideas we took from IPS is that system state can be modeled as a set of packages, and software installation, deinstallation can be modeled as a set of actions. And this kind of allows us to avoid a lot of complexity, because people are always like, oh, I need a graph now. Well, no, you don't really need a graph, because with software installation, deinstallation, everything always happens in the same order in both circumstances. We're not going to use any custom metadata formats, because no one wants to write parsers for your weird, fucked up metadata format. And our package versions are going to utilize a defined standard combined with a timestamp component. Now, that's important, because one of the things we've continually dealt with in regards to reproducing builds and segmenting our deployment environments, dev, staging, production. Sometimes we don't want to increment the version to signal that something has changed. We just want to roll this, and we don't want to maintain state. So ideally, a timestamp component being a first class citizen in the version is important, because we can just build. We don't have to worry about any complex versioning when we do our rollouts, and we can handle artifact promotion any way we want. Maybe we want to upgrade the main Semver version, or we can just go with the timestamp. That's fine. When we couple this, okay, our repositories are multi-vendor. That's kind of out of order there. When we couple this with adding these two channels in repositories, this creates a really powerful feature where I can pin systems to the pool, which is everything that gets into a repository, and that's going to get the latest, always the latest. So if you're just updating the timestamp, and again, the system handles the timestamp, you can have a group of systems pinned to the latest, and you can create channels within this pool. Channel is basically a view into the pool. So you can have your dev channel, you can have your staging channel, you can have your production channel, etc. And this can even be independent of what branch you're building from if you want. But it kind of solves that issue where devs deploy differently from operators, etc., and still allows us to, again, validate our environment. Our dev environment hasn't been tampered with. We know this cryptographically. Our staging hasn't been, etc. And this gets into the fast validation. So it should be easy and fast to validate and repair the integrity of an installed package set. So if I find a problem, I should be able to easily fetch just the thing that is broken and repair it. We're solving this in ZPS with an indexed archive format. So not only can we quickly extract files from inside the archive, but we don't even have to download the whole archive from HTTP in order to do this. We can use a range request and pull the file out of the archive after we fetch the header. So it's kind of neat. And a developer should never have to adopt a build system to build a software package. So if you're happy with Maven or Make or Rake or whatever you're using, then you should be able to use that. And in order to facilitate this, we have the command line option, so you can chain all your command line options together to generate a package. And we also have just a small package build DSL utilizing HashiCorp HCL. So that's kind of nice. So if you want, you can just throw an HCL file in your project and then build it, or use the command line. The package file format should be accessible to developers. It's very simple. It's just a binary header with the signed manifest appended, and after you read that, there's index compressed streams afterwards. And we should be able to generate images for container systems. And it should be as simple as just a list of packages. And this we're hoping that we can provide a way to create container images that can also be validated and are not subjected to the same, Dockerfile, bash mess that is out there now. We also want to support multiple installation routes. and do this by environment manipulation. So container technologies are not required, or optionally integrate with the native container sandboxing technologies on the platform. So this means that I don't have to cop out and use virtualization on Windows or on OS X, etc. This isn't actually that terribly hard to abstract. And in regards to like native code, it's pretty easy to manipulate the linker environment or manipulate these in the builds, and we can provide documentation on how to do this. So you can create, one root with whatever you want in it, and another root with whatever you want, etc. And the last one, our group is a real big fan of the HashiCorp toolset. So for future integrations, we want to provide like a policy integration system. So maybe when we install a package and it's flagged as a config file, we can ask to have this templated, like ask console template, for example, or some other service that acts as a gateway between the installation system and Vault or console or Nomad, perhaps. So we're really close to releasing milestone 1 of this. And milestone 1 is basically focused around the idea of an ancillary package manager. And this would be kind of like Brew. It doesn't manage the software root, but it gives you the other features in order to manage an image with your custom software in it. And this is kind of milestone 1. The entire purpose is to validate the concept and validate the usability requirements. And one of the core features, again, is multiple ZPS roots. We want to support Linux, OS X, and SmartOS. Windows isn't out of the question. It's written in Go currently, but I think I would need to find someone else to do the Windows implementation because I just don't care. So far, and I talked about actions, and I'm going to show you some of these in action. But these are the actions that have been implemented so far. We have metadata. So you can add custom metadata to your software installed set. So let's say I want to know the Git hash or whatever that can be in there. Or I just want to add metadata specific to my particular use case. I can do this, and it's easy. Files, directories, symlinks, that's all in there. Signature isn't quite done, but it will be there, and it's required to cryptographically validate the archive. Dependencies, obviously. Users, so this is one of the features of IPS is, software installation also includes adding, removing users that software requires to run. This is accomplished in RPM and apt in these crazy scripts. That's terrible. We don't want to have scripts running on package install and deinstall. So we're providing managed resources that will do this on each target platform. And also a service resource, which will integrate with systemd on Linux, or launchd on OS X, or SMF on SmartOS. Again, not terribly difficult to abstract. And milestone 2 is going to be basically focused on providing all the features that will allow us to operate as a root package manager. And this is going to be interesting because the test cases are basically going to be packaging these operating systems themselves. And FreeBSD is an interesting target because it's never really had, I think recently in 11 they added binary updates for the kernel and the user land, but historically you used to have to patch from source and build, and that's just sad in 2016. But again, the test case will be packaging these operating systems and providing a base that people can use either in containers or on their own. And the actions we want to add again is tags for files and a template action. So if you want to provide templates along with your software, that while installed will request templating and will precede the config that is also flagged from console template or whatever template manager you have, or maybe etcd, you can do that. And this is kind of coming from my hate of add-on config management. I think we can integrate the software installation system with our various sources of data and do it all at once and not have Chef and Puppet running as well. So just so you know, it's not vapor. I'll just show you a little bit of what we have here so far. So here we have my test directory. Actually, let me show you this first. So here's what a Z package file looks like right now. And this is just a HCL, DSL. These are meta actions. This is actually changed in the most recent version, but you can kind of see how it works. The meta actions basically describe the package metadata. And you can define file actions on your own if you want. If you want to composite, like let's say you had a build root and you wanted to composite, whatever you wanted, you could manually add these file actions. You don't have to do that, as we provide a file system walker that'll just do it for you. But you can override things like mode, owner, etc. But this is all you need, and these switches are also exposed on the command line. So if you just want to string something together, you can. So I'll just build a package really quick from my test package. So if I just execute build, it looks for the Z package file in the local directory and went ahead and did it. This is just a Apache Cassandra source tree that I'm turning into a package. And then it outputs it in the local directory. So then if I just go ahead and install it, it'll go ahead and go through the list of provided installs and remove the old one, install the new one. And you can kind of see how we're providing for cross-compile in the file name, cross-compile friendly file names, so we can just, for like Rust and Golang, we can just output all of our packages in one build. So we'll go ahead and we can list what's installed. I think I have some other, my snarf package installed, and that's important. Let's have a look at what the manifest looks like. So we take in HCL from the config file, and we generate the manifest that's part of the file format. And we can use this command to have a look at, what does the manifest look like. So there's a lot of files in here, so it's pretty big. But at the top, we see our package metadata. And then we see the file system actions. So all the directories are here. Then our files, and you can see that these are indexed. So after we read the manifest, we can skip around anywhere we want in the archive and pull these files out pretty quickly. And that's another interesting bit. No one's really developed an indexed archive file format that doesn't have the header at the end in the last 12 years. So we made one. So what else do I have? So yeah, we can also look at a friendly view, just your basic info from the package, etc. And that's about it. The big bit of work right now is just getting the dependency solver integrated. So I was working with James Nugent from HashiCorp on that. So after we get that working, milestone 1 will be pretty much ready to go. So hopefully we have that done by March. But that about sums it up. So So if you have questions, now is the time. I guess I can kind of look over here. Okay, so the top question, where can we find ZPS? Well, it's not quite ready for public consumption. I'm kind of afraid of the support burden, and the dependency solver doesn't work yet, so it's not out there yet. It will be on GitHub as soon as it is. I can use Ansible to build my Docker images. Yep, sure. Yeah. Auto increment ID. I suppose, sure. But it's also useful to know, when this thing was generated. So why not know that? Have you considered using Gen 2's portage? Actually, I didn't really look at it because portage is more. I guess I feel it's more of a build system than a package manager. But yeah. No, it isn't because my first name is Zachary. No. It was a play. It was a play on the whole ZFS thing. Well, no, this isn't necessarily targeted for containers. My biggest problem is that, and the reason why we were developing this is there hasn't been any innovation in the package manager space in 18 years. And we want to solve this. We want to solve this for single system installs, and we want to provide a structured way to create images for people that utilize containers, whether it's for Linux or SmartOS or, I think that's it. Why is packages defined not using JSON? Well, we use HCL, so if you want to use JSON, you can. The HCL, our parser will parse JSON as well. So yes, we want machines to be able to generate these packages as well. We just opt for the HCL to start because it's easy for humans to read and edit. So that looks like it for this. Does anyone from the audience have any questions? Vendoring dependencies for binary packages? That would seem to create kind of a hierarchy. So I feel the solve for that in the binary space is to just generate a separate image root. If you have specific things that need to go with this, you can, it's essentially the container image. But the great thing about a ZPS package root is that you don't have to use container tech. So you can just, there's the command that we're working on is called zenv, and you just use it to enter that root, and your environment's set up. The linker will be set up if you're using native code, but if you're using Java or whatever, it just works.
Would work something like Python virtual environment?
Right. But we don't really want to do, hierarchies of binary packages. That kind of should be dealt with in a different area. Anyone else? Cool, great. Thank you.